In this video, we're going to look at the assumptions needed to do a simple linear regression analysis. And for that, we need to understand what is the hypothesis testing, the statistical analysis that we're going to be doing. Here, for the regression model to be of any significance to us, the slope coefficient beta sub 1 must not be 0. It should be different from 0. If beta sub 1 is 0, it doesn't matter what x is, y is not going to be different, y is not going to change because of x. So if x is significant for determining y, for estimating y, then beta sub 1 must be different from 0. So the hypothesis that we'll be testing, the alternative hypothesis, is going to be beta sub 1, the slope coefficient, is not 0. The null will be beta sub 1 is equal to 0. And for us to be able to test that hypothesis, we need certain assumptions. So let's look at what those assumptions are. And these assumptions can be, we can remember the assumptions using the acronym LINE, L-I-N-E, linearity, independence, normality, and equal variance. So linearity is that there is a linear relationship between x and y, which is what we just saw. If the relationship between y and x can be expressed as y equal to beta sub 0 plus beta sub 1 x plus the error term, which is our simple linear regression model. Okay, so we have to assume that that is true. So that's linearity assumption. And then the error part, the e at the end, or epsilon, the Greek letter e, epsilon, they are statistically independent of x. So we are assuming that no matter what x is, the error term is not going to be determined based on the value of x. So x and error term are totally independent. Then the error terms, if you follow the probability distribution of the error term would randomly fluctuate according to normal distribution. Okay, with a mean of 0, the error term mean will be 0, and the variance that it will have will be the same irrespective of what the x is. Okay, x is independent of the error, so the variance of error will be the same irrespective of the x values, and that's the fourth assumption, equality of variance. So linearity, the model assumption, the errors are independent, and the error follows normal distribution, and the variance are all equal. So these are the four assumptions needed. And how do we verify that these assumptions are valid, or is there any reason for us to doubt that one or more of these assumptions is not true? And for that, we'll do what is called residual analysis. We take the residual, which is y minus y hat. So you have the actual y values, and you have the y hat value, which comes from our regression model. So if you go y minus y hat, that is the error term e. So we look at the error terms, analyze the error terms to see whether these assumptions are valid or not. So here is the error term, y minus y hat. Okay, and then we will do some graphical analysis of these residuals. So we plot the residuals versus x. You take the x values on the x-axis, and for each x, the corresponding residual will be plotted on the y-axis. Okay. Now, if the residuals have completely random pattern, so like this one, so they're all completely random. So that means the errors are completely independent of x's, and therefore the linear, not only the independence is verified, but the linearity is also verified. If there is a discernible pattern like these, so that means the error term still has some predictability left over. It is not completely random. The model has not captured some systematic variability from the errors. So the linear model is not adequate to extract all the estimatable information from the data. So if the model is sufficient, if the model has sufficiently extracted all the information from the data, then the residuals must be completely random, and if the residuals show a pattern like any one of these, the linearity assumption beta sub 0 plus beta sub 1 x model is not adequate, it is inadequate. Okay. Now, if the residuals are completely independent, once again you would see completely random pattern for the residuals, which is what I mentioned just a few minutes ago. Now, if the residuals have a pattern like this, so if it goes up and down, or it starts out negative and then becomes positive as x value increases or decreases, and these are cases where we see a cyclical pattern, and that would indicate that the errors are not independent of x. If you know x, you can predict what the value of error will be, so which means x and the errors are not independent. Now, for normality, we can use the test that we already saw in chapter 3, I believe. So you take the error values, do a box plot or stem and leaf plot, look at a histogram and see whether the histogram has a normal pattern, or you can do a normal probability plot and see whether the normal probability plot is on a straight line. So with these plots, we can verify whether the errors follow normal distribution or not. Okay, so something like this for normal probability plot would mean that the normality assumption is valid. And the last assumption, which is equality of variance, okay, you would see the residuals follow a random pattern of the same width no matter what the x values are. Okay, so here also the residuals fall within the same bandwidth. Okay, but here the problem, so here the variance is equal, but there is a problem in terms of model not being adequate because there is a linear pattern in the residuals. So this is a good pattern where there is no it's completely random and the fluctuations are within the same bandwidth across all values of x. Whereas if you see here in these two cases, the points are random, all right. Okay, the residuals are random. So the model assumption, the linearity model assumption is a valid one. But then you see the variability is not along a constant band, starts out small and it increases with increasing values of x. So the variance is not constant across all values of x. It is not equal variance. The residuals do not have equal variance with respect to x. Now let's look at these patterns with an Excel example.